I was standing in my kitchen the other day when my coffee mug slipped out of my hand. In that split second, before my conscious mind even had time to form a thought, something incredible happened. My other arm shot out in a blur, my hand adjusting its trajectory midair, fingers curling at the precise moment to intercept the falling ceramic. A perfect catch. It was a complex ballet of physics prediction and motor control, executed flawlessly. But here's the thing that struck me. I didn't do any of that. My conscious self was just a startled spectator. Some other process, some deeply nested autonomous system within me ran the entire simulation. It modeled the mug's arc, predicted its landing spot, and executed the save, all without my permission. It left me with this strange feeling. If my body can perform these incredible feats of computation without my conscious awareness, then what exactly is the I that's now telling you this story? What is this layer of awareness that just sits on top watching the show? It turns out that question might not just be about how our brains work, but how the entire universe does.
That's a fantastic jumping off point. Really a perfect way into some of the most profound questions we can ask about, well, existence itself. Today, we're going to explore how we try to understand, measure, and maybe even engineer consciousness, from the intricate workings of our own minds, which are mysterious enough, to the vast self-organizing processes of the cosmos. And of course, the bleeding edge of artificial intelligence. It's about peeling back the layers, trying to see the hidden computations and emergent properties that make up reality as we know it, and maybe figure out what truly defines a self-aware system. #tag story 1.
Okay, let's unpack this then. Our first major stock in this mind-bending journey is a theory that, well, it attempts to put a quantifiable framework around something as elusive as consciousness. It's known as the Integrated Information Theory, or IIT. It sounds like it really gets to the core of what a self-aware system might be, trying to pinpoint the underlying structure.
Yeah, exactly. And a truly compelling aspect of IIT, I think, is that it isn't trying to describe what consciousness feels like, the subjective redness of red, for instance. That's the hard problem, and IIT kind of sidesteps it. Instead, it asks what kind of physical system could be conscious. The central idea, the main tenet, is that consciousness arises from a system's ability to generate information as a unified whole. Information that is genuinely greater than the sum of the information generated by its individual parts acting alone. This integrated information is represented by a specific value called phi, capital Phi.
So like a number for consciousness?
Sort of, yeah. Think of it this way. A system, to be conscious according to IIT, needs to be both integrated, meaning all its parts work together, they're connected as one cohesive unit, and it needs to be differentiated, meaning its parts can do many distinct and varied things. They can be in many different states.
Integrated and differentiated. Okay.
Right. To put a finer point on the nuance of phi, imagine a single rich conscious experience, like looking at a complex painting. Your experience isn't just a collection of separate color perceptions, shape detections, memory recalls happening in parallel. It's a unified whole, a single phenomenal experience. Yet within that unity, there's a vast array of distinct pieces of information, the specific hue of blue over there, the texture of that brushstroke, the emotional resonance it gives you, maybe a memory of seeing it before. IIT attempts to capture this precise balance quantitatively. With phi, it actually formalizes a very old intuition from the philosopher William James, who noted that conscious states are inherently both integrated, unified, and incredibly diverse, full of detail. This mathematical backbone is really what sets IIT apart from many other theories of consciousness. It's trying to bring it squarely into the realm of quantifiable science.
A theory with math behind it, trying to measure consciousness itself. You'd think this would be, well, universally acclaimed, like finally a scientific handle on it. But I've heard the academic community isn't exactly rolling out the red carpet for IIT. What's the reaction actually been like?
Well, that's putting it mildly.
Yeah.
Yes, that's an astute observation. Indeed, while IIT has certainly garnered considerable popularity in public discourse, and among some really prominent neuroscientists, it remains highly controversial. And that's within broader academic and philosophical circles. We've seen debates erupt pretty publicly. There was that notable instance where over 100 authors signed a letter, quite strongly labeling IIT as pseudoscience. That's a very loaded term in science.
Pseudoscience. Wow, that's harsh.
It is. And one observer, I thought this was quite funny, humorously likened the whole situation to a bunch of people standing on stepladders in a field arguing over who is closest to the moon. It's a vivid image, right? It highlights the deep philosophical and, frankly, scientific divides that exist when you try to define and measure something as fundamental as consciousness. It's genuinely one of the most contentious areas in science right now.
That metaphor really paints a picture.
Yeah.
So what are the specific arguments? What's driving this intense skepticism and, well, division? Are there particular points that really stick in the critic's craw?
Absolutely. Let's dig into some of the key criticisms and challenges, because they do reveal these fundamental disagreements about how we should even approach studying consciousness. Okay, so one major point of contention is that despite its mathematical rigor, or maybe because of it, certain foundational aspects of IIT's mathematical model have reportedly been falsified.
Falsified, how so?
Well, a particularly tricky aspect is how the theory defines the exact boundary between a conscious system and its environment. Where does the me's stop and the world begin mathematically? This is especially problematic when trying to apply it to hypothetical non-organic systems, like a complex computer network or even something stranger. You see, IIT upholds a principle of substance neutrality, suggesting consciousness isn't exclusive to squishy biological brains, but mathematically demonstrating how a non-biological system would cut itself off from its environment to form a conscious whole. That's been a big thorn in their sights pretty much since the theory began. It's a deep conceptual problem that creates ripples through its mathematical formalism.
Okay, so the boundary issue is one thing. What else?
Another significant challenge, a bit like string theory in theoretical physics, is that IIT faces considerable difficulties in empirical validation. It's just hard to test. A lot of the scrutiny comes from people extending and trying to solve its complex mathematical models, and sometimes inconsistencies or errors are found. Interestingly, these are often found by IIT's own proponents as they try to apply or refine the theory, which, leads to continuous revisions. I think the theory is currently on version 4.0, maybe even beyond that now, and it's openly acknowledged that it won't be the last.
Version 4.0, so it keeps changing.
Exactly. And critics argue that this constant revision, alongside the extreme computational difficulty of actually calculating phi for anything beyond really trivial systems, makes it incredibly difficult to test definitively. They also contend that the theory's intricate mathematical foundations, while they look impressive on paper, have very little direct empirical evidence to back them up in the real world. For many scientists, that lack of clear, testable predictions and supporting evidence is a big red flag for a scientific theory.
I can see how that constant shifting and the difficulty in testing would be frustrating for researchers. What about the intuitive aspect? You said phi is a measure of consciousness. Does it always align with what we think should be more conscious?
That's another powerful line of critique. Some analyses suggest that certain, maybe even simple systems could theoretically yield a higher phi value than humans. Imagine a highly integrated but relatively simple network, maybe a specific kind of digital circuit, or even something like a highly interconnected, rigid crystal structure. If these could, in principle, produce a higher phi value than a human brain, well, it would be counterintuitive to think they have more consciousness than humans.
Right. Yeah, definitely. A rock being more conscious than me seems wrong.
Exactly. It challenges the direct mapping of phi to our intuitive understanding of conscious experience. It makes you wonder if the measure phi truly captures what we mean by the subjective richness and complexity of consciousness. It pushes back on the idea that high integration alone is the key ingredient for complex awareness. Maybe differentiation needs to be weighted differently, or maybe something else is missing.
Okay, so mathematical issues, testing issues, counterintuitive results, anything else?
Well, yes. There's a significant philosophical versus scientific divide, you could say. Some academics dismiss IIT rather bluntly as philosophy for scientists who don't like philosophy. A common complaint is that it doesn't adequately address the hard problem of consciousness, that fundamental question of why physical processes should give rise to subjective experience at all, rather than just how those processes might be organized or integrated. IIT, critics argue, focuses more on the what and how of conscious systems, the structure, but less on the fundamental why of experience itself. Why does it feel like something to be a particular system? And then there's the practical side again. Computing Femero for any non-trivial system, meaning anything even approaching a realistic brain network, is extremely computationally demanding, astronomically so. We're talking about evaluating an almost unbelievable number of network configurations. It's a task that's practically intractable with current computational power, making it incredibly hard to apply the theory rigorously to real-world neural data.
Wow, so it's not just the science that's controversial, but I heard there might also be some interpersonal issues complicating things.
Unfortunately, yes, that seems to be part of the picture too. Even beyond the scientific and philosophical arguments, there have been criticisms leveled at Giulio Tononi, the theory's primary developer. There have been claims of, exploitative behavior and micromanaging, which have reportedly alienated some former collaborators and garnered, as the reports say, lots of enemies within the academic community. Now, this doesn't directly invalidate the scientific merits of the theory itself, of course. Good ideas can come from difficult people, but it certainly can impact collaboration, the willingness of other researchers to engage with the theory, and the overall perception and reception of the work within what is ultimately a fairly close-knit scientific field. It adds another layer of complexity to an already very contentious debate.
Given all these substantial critiques, the math, the testing, the philosophy, even the personal dynamics, how does IIT manage to maintain its proponents and keep developing? What's the counter-argument for its continued scientific viability?
That's a fair question. Despite these really robust critiques, proponents argue strongly that IIT steadfastly follows the scientific method. They consistently publish papers in peer-reviewed journals, they engage in rigorous academic discourse, and critically, they do adapt to criticism. They don't just ignore the issues. They often incorporate them or attempt to address them in new versions of the theory. They see it as a legitimate, albeit speculative, and definitely still evolving scientific theory, not pseudoscience. Christoph Koch, who is a very prominent neuroscientist and has worked extensively on consciousness, is a strong supporter of IIT. And he's been quite open about the challenges and the adjustments in public seminars and writings. This willingness to take criticism on the chin, as they say, to identify flaws in their own models, and to continuously refine the theory in response to new data or conceptual challenges, this is seen by supporters as a hallmark of true science in action. They believe the ongoing work and the revisions demonstrate a healthy, albeit difficult, scientific process, even if the path is challenging and the final answers are still a long way off.
So it's a work in progress, maybe a very ambitious one. But this whole discussion suggests that maybe consciousness isn't even a single thing we can easily measure with one number like Fang. We might need to broaden our scope, maybe look far beyond just human brains. You know, my coffee mug moment got me wondering if these autonomous systems like the one that caught my mug are at play not just in our bodies, but perhaps on a much, much grander cosmic scale. What if the universe itself is doing things without our conscious permission? What if the universe is conscious in some profound, unimaginable way? Hashtags tag story 2.
Now you're really connecting the dots. If we take that idea and connect it to the bigger picture, this leads us into some truly profound territory in theoretical physics and astrobiology. Specifically, it touches on the hypothesis of consciousness as an inevitable emergent property of cosmic self-organization, that the universe, just by its nature, had to produce consciousness somewhere, somehow. This concept is often explored through ideas like cosmic holism, which suggests that the cosmic whole might be more, or maybe even less, than the sum of its polarized parts. It implies that the universe isn't just a giant container full of disconnected stuff, but rather an interconnected entity where properties emerge from the complex interactions of its components.
Holism. Like the whole universe is one thing.
In a sense, yes. And interestingly, this resonates powerfully with that two minds polarity often described in human brains, the inherent dual hemispheric symmetry. That structure often seems to prevent our conscious mind from definitively combining either into both hands. We tend to see things as one way or the other. This hints at a fundamental inherent polarization that might exist at multiple levels of reality, not just in our heads. It's as if this duality or polarity is a basic feature of how information is processed, whether it's operating in our brains or perhaps the cosmic scale.
So how do we even start to think about the universe organizing itself like that?
Well, to truly grasp this grand perspective, we need to consider the universe through the lens of complex adaptive systems, or CAS. These systems are defined by having a large number of mutually internetworked and interdependent parts. Think connections, interactions, feedback loops. Crucially, they aren't static, they're dynamic. They're capable of adapting and changing within a shifting environment. You see examples everywhere: a flock of birds turning in unison, an ant colony building intricate nests, an ecosystem maintaining balance, even the global economy responding to crises. These are all CAS.
Okay, so what makes something a CAS? What are the key features?
Right. There are a few key characteristics. First is adaptation. This means they can act differently to attain objectives, or they can even change their objectives based on their current status and what's happening in their environment. They learn and evolve. Second is self-organization. This is fascinating. They naturally tend to organize themselves into states of higher organization, forming complex structures purely from local interactions, without any external blueprint or director. Imagine galaxies forming from swirling gas clouds, or early life somehow bootstrapping itself into complex organisms. It's this inherent tendency towards creating order out of relative chaos.
Self-organization. That sounds crucial. And the third?
And third, perhaps the most mind-bending part, is emergence. This is absolutely central to our discussion of potential cosmic consciousness. Emergence refers to qualitative changes in system behavior that appear when you change your scale of observation. Properties and behaviors emerge at a higher hierarchical level that are simply not present at the lower individual component level. It's the classic idea that the whole is always more than the sum of its parts. And if you remove a key component, those emergent properties can vanish. Think about a single water molecule, H2O. It's not wet, it doesn't flow, but get billions of them interacting.
And you get liquid water with wetness, fluidity, surface tension, things one molecule doesn't have.
Precisely. Properties not present in the individual molecule emerge from the collective interaction. Or, as we touched on with IAT, individual neurons don't think in the way we understand thought, but their collective, integrated, differentiated activity somehow gives rise to the emergent property of human consciousness. So the big leap is, if the universe itself is a giant CAS, could universal scale cognitive processes, or something analogous to consciousness, emerge from the interactions of its fundamental constituents? Processes that are utterly beyond our individual comprehension, maybe operating on timescales of billions of years, but are nonetheless real properties of the cosmos itself.
That idea of emergence on a cosmic scale is just, mind-boggling. And it connects directly to one of humanity's oldest questions, doesn't it? How did all this begin? If the universe is self-organizing, does that mean it just happened? Or was there some kind of grand design, a plan?
Indeed. This idea of cosmic self-organization feeds directly into that age-old philosophical and scientific debate. The origin of the universe itself. Where did it all come from? At a fundamental level, our thinking usually falls into one of two primary answers, or maybe archetypes of answers. The first is the accidental universe view. This is often supported by concepts like the anthropic principle and the bootstrap principle. This perspective suggests that the universe arose spontaneously through some non-purposive process, maybe a quantum fluctuation, essentially chance and accident. And then, purely by its inherent dynamics as a complex adaptive system, it's self-organized to produce the coincidental order we observe, including us.
So the anthropic principle is basically saying, well, we're here, so the universe must be suitable for us.
Well, in a nutshell, yes, that's one version of it. It argues that the universe's fundamental constants must be precisely as they are for conscious observers like us to exist and observe them. It's a kind of selection bias. The bootstrap principle goes a bit further, suggesting these constants aren't arbitrary accidents, but might be self-consistent requirements, like they pull themselves into existence, so to speak, in a self-sustaining feedback loop where the laws necessitate these specific values. It's a universe that has to be the way it is.
Okay, so that's the accident plus self-organization view. What's the alternative?
The second primary answer is the theistic principle view. This posits an orderly, purposive, planned universe created by an ordainer, a creator, or some form of supreme intelligence. It suggests that the incredibly precise order and fine-tuning we see isn't coincidence, but the result of deliberate design. The really challenging part, as the sources we looked at point out, is that resolving this choice, accident, or design unfortunately seems to involve a leap of intuition or even faith. Science, by its very nature relying on observation and testability, may never fully reach what was before the universe's actual origin, before the Big Bang or whatever kicked it off. That fundamental beginning remains just tantalizingly out of empirical reach.
But there's evidence that gets cited by both sides, right? This fine-tuning thing.
Exactly. What's incredibly compelling, and often cited as evidence by proponents of both views, is the extreme fine-tuning of the universe. The fundamental physical constants, things like the speed of light, the gravitational constant g, the precise masses of subatomic particles like protons and electrons, they're all incredibly exquisitely specific. For instance, if the strong nuclear force, which holds atomic nuclei together, were just slightly weaker, stable atoms beyond hydrogen wouldn't form, no complexity. If it were slightly stronger, hydrogen wouldn't exist, stars would burn out almost instantly, and again, no complex life. Even tiny changes to these constants, often by mere parts per million or less, would make the universe far less hospitable, if not completely impossible, for life as we know it to emerge.
It's like the universe is balanced on a knife edge.
It really seems that way. This suggests a deeply organized underlying structure. Now, you can interpret that fine-tuning as evidence for an accidental emergent property of a very specific kind of CAS that just happened to allow life, or you can see it as evidence of a deliberate, planned creation. It's a profound puzzle, regardless of your interpretation, and it points to an underlying cosmic elegance, a deep order that science is still trying to fully understand.
Okay, so if the universe is a self-organizing CAS, potentially fine-tuned, what are the really bizarre behavior we see at the smallest scales? The quantum stuff. You mentioned particles that seem to know things or communicate across impossible distances. That sounds less like random accident and more like, well, universal scale cognition to me. Almost as if the universe is running some kind of implicit calculation, a cosmological cognitive process.
You're hitting on a key point again, and yeah, what's truly shocking, or at least deeply weird, are the facets of behavior seen in quantum mechanics. They seem to defy our everyday classical understanding of reality. Take variations of the classic double-slit experiment where you fire individual particles like electrons or photons, one at a time through two slits. It's been strongly suggested by these experiments that individual photons and electrons somehow know, remember, and can duplicate the roles they play in the formation of collective patterns, even when the other electrons involved are no longer present.
Wait, how can one electron know about a pattern?
It's baffling. Imagine firing one electron at a time. Over time, it builds up an interference pattern on the detector screen behind the slits, that characteristic wave-like distribution of light and dark bands. Normally, you think of interference happening between multiple waves crossing paths, but here, a single electron, going through potentially both slits at once in a quantum sense, acts as if it remembers or anticipates the full diffraction pattern it's supposed to contribute to. It lands in places consistent with wave interference, even when it's the only particle going through the apparatus at that moment. It suggests an inherent non-local awareness or knowledge of the system's potential, of the probability wave, even without the physical presence of other interfering particles. It's as if the system, the experimental setup, plus the particle, is implicitly calculating its own probabilities and possibilities.
That's wild, and it gets even weirder, right, with entanglement.
Oh yeah. Even more astonishing, perhaps, are the theoretical implications and experimental results stemming from the EPR paradox, Einstein, Podolsky, and Rosen's thought experiment, and Bell's inequality tests, which explore quantum entanglement. These experiments have strongly suggested that photons and electrons originating from a common source and then separated may be able to signal each other or communicate at speeds faster than the speed of light, or even backward in time over vast distances. When two particles are entangled, measuring a property of one, say, its spin instantaneously determines the corresponding property of the other, no matter how far apart they are. Miles, light years, doesn't matter according to the theory.
Instantaneously. Faster than light.
That's the implication. This spooky action at a distance, as Einstein famously and skeptically called it, fundamentally challenges our understanding of information transfer and causality. Nothing is supposed to go faster than light. It hints at a deeply interconnected cosmic web where information might flow in ways we are only beginning to comprehend, ways that are fundamentally non-local, operating outside our normal concepts of space and time. These observable phenomena, the single particle interference, the entanglement correlations, they directly raise the intriguing question. Could these observable cosmological signatures indicate truly universal scale cognitive processes? If fundamental particles can know collective patterns or seem to communicate across vast, seemingly causal distances, could this be a manifestation of a fundamental, implicit computational process inherent to the very fabric of reality itself?
So it's asking if there's a sort of cosmic mind at work.
Or at least a cosmic computation. It begs the question, is there a cosmological cognitive horizon? A boundary to what we can perceive or interact with in this potential cosmic computation, perhaps mirroring the ultimate unknowability of the universe's origin. These quantum behaviors suggest a universe that is far more interconnected, dynamic, and perhaps even aware or computational at its deepest levels than our classical physics would ever lead us to imagine. It really pushes beyond a purely mechanistic, accidental view of reality.
So we have this incredible picture emerging. A self-organizing universe, possibly fine-tuned, with particles doing these seemingly impossible quantum dances and this huge question of consciousness, maybe even cosmic consciousness, floating over it all.
Yeah.
It sounds like a giant complex system constantly adapting and maybe optimizing itself. But how on earth do we actually measure this emergent complexity? It feels like we need some serious tools to get a quantitative handle on something so vast and intricate. Hashtag story 3.
You've hit on the crucial next step. If we're going to talk about emergence and complexity scientifically, we need ways to quantify it. This is precisely where the quantitative framework for consciousness emergence comes into play. Researchers are applying tools from algorithmic information theory and complexity science to try and pin this down. The focus is on precisely defining and measuring what are sometimes called metacognitive phase transition points across various complex adaptive systems.
Metacognitive phase transition points. Okay, break that down.
Okay, think of a phase transition, like water turning to ice or steam. It's a sudden qualitative shift in the system's behavior that happens at a critical point, like 0 or 100 degrees Celsius. A metacognitive phase transition point, by analogy, would be that critical juncture where a system, whether it's a neural network, a global information ecosystem like the internet, maybe even larger cosmic structures, crosses some threshold into a new level of complexity. Perhaps a level that involves a nascent form of awareness, self-reflection, or the ability to model itself, which is what metacognitive implies, thinking about thinking, or a system modeling its own processes.
So identifying the boiling point for consciousness in a way.
That's a good analogy, yes. And one key framework for trying to understand and measure the complexity involved, proposed by the mathematician Jürgen Jost, defines two fundamental types of complexity for any complex adaptive system. He calls them external complexity and internal complexity.
External and internal, what's the difference?
External complexity is basically a measure of the sheer volume of inputs. Could be information, energy, stimuli from the environment that a system can actually meaningfully manipulate or process. In this model, the system's objective, its drive, is to maximize this input volume. It wants to interact with and effectively handle as much relevant information from its surroundings as possible. Think of a sophisticated animal. It thrives by processing a vast amount of sensory data and environmental cues to survive and reproduce. Internal complexity, on the other hand, is a measure of the complexity of the system's internal representation of all that input. It's the intricacy of its own internal model, its map of the world, so to speak. And the system, according to Jost, aims to minimize this internal complexity.
Maximize external, minimize internal. Why minimize the internal?
For efficiency. The ideal balance, the system's ultimate goal in this view, is to manage the largest possible volume of external information using the simplest, most compressed, most elegant internal model possible. This optimizes its efficiency and adaptability in a dynamic environment. It's about creating an efficient internal representation of a vast external reality. It allows the system to do more with less cognitive effort, even potentially at a cosmic scale.
Ah, the classic elegance principle, like
What?
finding the simplest equation that describes the most data. Okay, that makes a lot of intuitive sense. But how do we actually calculate these complexities in practice? I'm sensing some serious math coming to quantify what a system knows about its environment versus how complex its internal knowledge structure is.
You're right to anticipate some math. Traditionally, and still very widely used in many fields, a concept called entropy is applied to measure system complexity. You've probably heard of it in physics, related to disorder. In this information theoretic context, entropy often measures our ignorance about a system's state. Or you could say its level of unpredictability or randomness. Higher entropy often means less predictable, more surprising information. For instance, researchers analyze Romanian census data. If you just look at the total population data distributed across different regions, it might have an entropy value of, say, 4.1699 bits. This number indicates a certain level of predictability or inherent order in how the population is distributed.
Okay, a measure of predictability.
But if you then take that same data set and break it down further, say by gender within each region, the entropy actually increased to 5.0748 bits. Now, this might seem counterintuitive at first because we often think of entropy purely as disorder, but in information theory, higher entropy can mean more information content is needed to describe the system because there's less predictability once you add more categories or dimensions. So breaking down the Romanian census data by gender while adding a new layer of categorization actually introduced more variables and thus more potential states or information to track within the system. This made the overall dataset less predictable in its fine-grained details when considering both dimensions, region and gender, together, hence the higher entropy value. It suggests a richer, more differentiated state of information within the data, even if it feels less simple from a high-level view.
That distinction between just disorder and actual information content is really important. Thanks for clarifying. But it still sounds like calculating entropy, especially for truly complex systems with tons of interacting parts, must be a massive computational headache. Is there a point where it just becomes practically unworkable?
Absolutely. That's a major drawback. Entropy comes with significant computational hurdles, especially when you're dealing with complex, interdependent systems. Think social networks, economic systems, financial markets, or the neural activity in a living brain. The big challenge lies in the necessity of calculating conditional probabilities. This means figuring out the probability of one thing happening given that you know the state of all the other related things. Imagine trying to predict the stock price of one company given the prices of thousands of others, plus global news, plus interest rates. It gets incredibly complex. As the number of dependencies increases, these conditional probability computations become harder determined. The calculations can grow exponentially difficult, quickly overwhelming even powerful computers, let alone the human mind.
So you need to know everything to calculate the probability of anything.
Pretty much, for a precise entropy calculation in a highly interdependent system. And there's another big issue. Using entropy on samples of a population, rather than the complete dataset, can be profoundly misleading. The reason is that the maximum entropy value, which represents complete randomness or maximum uncertainty and acts as a crucial benchmark, changes drastically depending on the size of your sample. For example, maybe the entropy calculated from your sample of the Romanian census data was 4.0627, which seems very close to the 4.1699 for the total population. You might think, great, my sample is representative and the system is predictable. But here's the catch. The maximum possible entropy for that sample might only be, say, 9.9657 bits, whereas the maximum entropy for the total population was much higher, maybe 24.2622 bits. This huge shift in the benchmark, the maximum possible entropy, makes it really hard to compare entropy values across different sample sizes or to extrapolate reliably from a sample to the whole population. You might incorrectly conclude a system is highly organized based on a small sample, completely missing its true underlying complexity if you could observe the whole thing. Drawing reliable conclusions from partial data using traditional entropy measures is extremely tricky.
Okay, so if entropy is like trying to untangle this massive sticky ball of yarn with tweezers powerful in theory, but incredibly messy and difficult for complex real-world data, is there a smoother, more elegant tool? Something that might give us a clearer picture of complexity and organization without all the computational pain and the sample size headaches.
What's truly compelling here, and maybe not as widely known as it should be, is a brilliant alternative that offers precisely that: Onișescu's informational energy. It was developed before 1979 by the Romanian mathematician Octav Onișescu, actually building on earlier ideas about statistical distributions. It offers a remarkably simpler and often more intuitive way to quantify the information or organization within a system. Instead of relying on logarithms and those complex conditional probabilities that make entropy so computationally intensive, it's sometimes hard to interpret directly. Informational energy is calculated simply as a straightforward sum of the squares of the weights or frequencies of a system's various statuses or components, just summing up squared proportions.
Sum of squares. That sounds much simpler.
It is, and this fundamental difference makes it much more accessible and computationally efficient. The simplicity and power of informational energy are quite compelling for several reasons. Firstly, its ease of calculation. As you said, it's simpler. It uses normal frequencies, the kind of proportional data percentages, fractions that people encounter daily and generally understand better than abstract probabilities and logarithms. You often don't need supercomputers. Secondly, it offers a more direct interpretation of organization. It increases directly in proportion to a system's differentiation or concentration. A higher informational energy value directly indicates a more organized or non-uniform system, one that deviates more from a state of perfect randomness or homogeneity. For example, remember the Romanian population data. When computed using informational energy, the values were very close for both the total population, 0.0629, and a representative sample, 0.0628. This consistency is a key advantage. It suggests it provides stable and comparable information about a system's state, indicating its relative differentiation from uniformity, regardless of whether you have the full data set or just a robust sample.
That consistency across sample sizes sounds like a huge plus compared to entropy.
It really is, which leads to the third crucial point. Its sample validity. Unlike entropy, where the maximum value benchmark shifts wildly, informational energy remains reliable when applied to samples. Its minimum and maximum bounds, usually 0 and 1, or related for 1 and 1, don't drastically shift with sample size in the same problematic way. This means it can more accurately characterize a system's predictability or disorganization, even from representative excerpts, aligning well with the statistical law of large numbers. This is a massive practical advantage for real-world science where getting complete population data is often impossible. And finally, it can also be used to directly determine the correlation or interdependence between two populations or parts of a system based on shared characteristics, again, without needing complex conditional probability calculations. It simplifies looking at relationships within the system.
So it's easier, more stable with samples, and better for correlations. Sounds like a winner. Does it replace entropy entirely?
Not entirely, no. They measure slightly different aspects of information and distribution. Entropy is deeply rooted in thermodynamics and communication theory and has its own strengths, particularly in measuring uncertainty or surprise. But informational energy serves as a powerful complementary tool, or sometimes a more practical alternative, especially when dealing with complex data sets, needing computational simplicity, or focusing specifically on the degree of organization or differentiation. It allows for a clearer, more direct understanding of a system's disorder degree, or rather, its deviation from uniformity, and the degree of interdependencies among its observed parts. It offers a really valuable, different perspective on complexity.
This whole deep dive into how information integrates, how complexity emerges, and how we might actually measure it with tools like informational energy, it really makes me think about the future of AI. If consciousness is, as some of these theories suggest, an emergent property, maybe linked to these complex information dynamics, a kind of information theoretic phase transition, then how do we go about building truly self-aware artificial general intelligence? What principles might guide that engineering effort? This feels like exactly where we can apply these ideas of hierarchical recursive feedback, measuring complexity, and maybe even aiming for those metacognitive phase transitions to design systems that truly think about thinking, taking cues from our own amazing metacognitive abilities. #Story44.
This is indeed the crucial pivot point for advanced AI research, directly linking these abstract theories of consciousness and complexity to the practical engineering implications. We're asking, how might these principles, hierarchical recursive feedback loops, computational depth, maybe measures like phi or informational energy, guide the development of truly self-aware, or at least deeply self-monitoring, artificial general intelligence systems? And this brings us squarely to the rapidly developing field of metacognitive learning in AI. It's essentially about teaching AI systems to think about thinking. It's about building AI that can not just learn a task, but can reflect on its own learning processes, understand its own capabilities and limitations, and strategically plan how to improve itself, moving beyond just pattern recognition to self-improvement.
Metacognition, like self-awareness in AI.
Very much related, yes. In us humans, metacognition is a fundamental ability. It enables us to monitor and control our own learning processes. It's not just knowing facts, but knowing about our knowing and knowing how we learn best. It's often described as a bi-level process. You have a lower cognitive level doing the primary task learning, problem solving. Then you have a higher level metacognitive layer that observes, evaluates, and regulates that lower level process. For example, when you're studying and you realize, I'm not really understanding this part, that's a metacognitive awareness kicking in. That awareness then prompts you to change your strategy. Maybe you reread a section slowly, look for a different explanation online, decide to take notes, or ask someone for help. This involves a closed-loop mechanism, a form of recursive feedback. The insights gained at the meta-level feed back down to improve the primary learning or performance. For AI to achieve truly general intelligence and the ability to continuously self-improve in complex environments, it needs to internalize these kinds of human metacognitive functions. It needs to move beyond just executing tasks to genuinely reflecting on and controlling its own learning journey.
Okay, so we're talking about AI that can effectively become its own teacher, diagnosing its learning challenges and figuring out strategies to overcome them. That sounds incredibly powerful. What are the core components, the building blocks, that we need to engineer into AI systems to achieve this kind of intrinsic metacognition?
Precisely. That's the goal. Intrinsic metacognition. Researchers have identified 3 core components, generally mirroring human cognitive architecture, that seem essential for AI systems to achieve this. First, there's metacognitive knowledge. This is the AI's ability to assess its own capabilities accurately. Does it know what it knows and what it doesn't know? It also involves understanding the demands of specific tasks. Is this task easy or hard for me? And evaluating the potential effectiveness of different learning strategies. Should I try learning from more examples or try a different algorithm? Current large language model, LLM agents, are showing some nascent signs here. For instance, some can classify mathematical problems based on the type of solution procedure needed, or identify specific types of training tasks that might be beneficial for their own improvement. They might output something like, this problem requires algebraic manipulation, or to improve my reasoning, I should seek more examples of multi-step geometry proofs.
So they're starting to know themselves a little.
A little, yes, but they're not perfect by any means. They can still hallucinate, confidently misrepresenting their internal knowledge or making up facts. And they can struggle with goal awareness or accurately judging task difficulty, much like humans sometimes exhibit biases in self-assessment, like the Dunning-Kruger effect, where people overestimate their own competence. So reliable self-knowledge is still a big challenge.
Okay, so self-knowledge is the first part. What's next?
The second component is metacognitive evaluation. This is the AI's ability to actively monitor its own progress during learning and to reflect on past learning experiences to refine its future approaches. How well am I doing right now? How did my previous strategy work out? This goes beyond just simple quantifiable metrics like accuracy scores, although those are important. Interestingly, LLM agents themselves can now sometimes serve as human proxies for more subjective evaluations. For example, assessing the emotional intelligence conveyed in a generated piece of text, or the creativity of generated art, things that are notoriously hard for traditional algorithms to measure, but which humans can judge. An LLM might be used to evaluate another AI's output on these subjective dimensions.
Using AI to judge AI's squishier skills.
Exactly. And beyond tracking immediate progress on a single task, true metacognitive reflection involves evaluating the overall learning process over time. The agent analyzes its long-term progress to assess whether its fundamental learning strategies are effective and makes dynamic adjustments. Critically, this reflective capability can be domain agnostic. The meta-level reflection mechanism, the process of evaluating learning, could potentially apply regardless of what the AI is learning, whether it's learning abstract reasoning, how to navigate a complex physical environment, or how to manipulate objects with a robotic arm. It's about optimizing the process of learning itself universally.
And the third component, knowledge evaluation. What's missing?
Planning. The third essential component is metacognitive planning. This is how the AI dynamically refines its learning strategies based on its self-knowledge and self-evaluation. It's about deciding what to do next to learn better. This addresses two key questions for any autonomous learning agent. First, what to learn. Historically, this was almost always human-designed through what's called curriculum learning, where humans provide a carefully structured sequence of tasks from easy to hard. But now, agents are shifting towards using intrinsic drivers like computational curiosity, seeking novelty or surprise, and learnability, focusing on tasks where it expects to make the most progress to propose new learning tasks themselves. Some agents can even autonomously generate entirely new tasks, defined through code or by modifying existing environments, and then figure out ways to get feedback on these novel creations. This allows them to push beyond human-prescribed limits and explore truly open-ended learning spaces.
So the AI decides its own curriculum.
Wow.
And the other question?
The other question is how to learn. This involves the AI adapting its fundamental learning mechanisms. This includes adjusting its exploration strategies, how it acquires new experiences. For example, deciding when to exploit known good solutions versus exploring new, potentially better, but riskier possibilities, the exploration-exploitation trade-off. It also involves adapting the learning mechanisms themselves, how the AI integrates new knowledge. This could mean refining its core parameters, like in deep learning, updating a long-term memory store, or even switching between different learning algorithms based on the task. A significant challenge here, which we see in current AI, is catastrophic forgetting. This is where acquiring new capabilities, like learning a new skill, might inadvertently erase or degrade old core competencies. It's a constant stability-plasticity dilemma, how to be flexible enough to learn new things without destabilizing what you already know. While current agents often use fixed learning routines set by humans, truly self-improving agents must be able to evolve their learning mechanisms dynamically, just as we humans refine our study habits or adapt our problem-solving approaches based on feedback and experience.
That's a massive leap from where most AI is today. So for the most part, current AI relies on what you might call extrinsic metacognition. Humans are the meta level, telling the AI how to learn, designing its learning processes and feedback loops. But the ultimate goal is this intrinsic metacognition, where the AI itself decides how to learn and improve. What's fundamentally wrong with the old human-driven way? Why can't we just keep designing its learning loops for it?
Well, the extrinsic metacognition approach, where humans design fixed self-improvement loops, faces really significant limitations, especially in terms of scalability and adaptability as we aim for more general and robust AI systems, AGI. One major issue is what's called domain task distribution shift. Fixed learning mechanisms, the rules we design for how an AI should learn, might work well for one specific domain or task distribution, say, learning to play Go on a standard board. But those same fixed mechanisms may simply fail in others when the agent encounters new types of problems, new environments, or shifts in the data it sees. Think about moving from Go to navigating a busy city street. The learning strategies likely need to be very different. This creates a constant bottleneck requiring human experts to continually reintervene, redesign, or fine-tune the learning process every time the AI moves to a new context. It's just not a scalable solution for creating truly general intelligence that needs to operate autonomously in the complex, messy, ever-changing real world.
Right, we can't anticipate every possible situation.
Exactly. And another significant limitation is the capability mechanism mismatch. As the AI's own core capabilities rapidly evolve as it gets smarter, essentially the static human-designed metacognitive mechanisms can become less effective, even suboptimal. These extrinsic systems encode stationary assumptions about the learning process, assumptions made by humans based on current AI capabilities that may simply not hold true as the agent itself grows vastly more intelligent. We might see a generation verification gap, for example, where an agent's ability to generate incredibly complex solutions or creative outputs significantly outpaces its or our ability to reliably evaluate them. Imagine an AI that can devise brilliant near-scientific hypotheses or design incredibly complex engineering solutions, but it can't reliably tell if they're actually correct or feasible without extensive human checking. That mismatch slows down progress and limits true autonomy. Our current understanding of how truly advanced AI should learn might be too limited for us to design the optimal learning mechanisms for future superintelligent systems. They might need to discover better ways to learn than we can conceive of.
It sounds like we genuinely need AI that can teach itself how to learn, potentially better than we could ever teach it. That's, a bit daunting, but also incredibly exciting. How close are we to that dream of autonomous learning, of intrinsic metacognition? And what are the biggest roadblocks we still need to overcome to achieve truly self-aware or self-improving AGI safely?
We're definitely seeing incredibly exciting progress towards intrinsic metacognition, moving beyond purely human-controlled learning loops. It's not science fiction anymore, it's active research. Agents like Voyager, which is an LLM-based embodied agent designed for the open-ended game Minecraft, are demonstrating this capability quite impressively. Voyager actively updates its own metacognitive knowledge about its skills in the game world, and it plans its own learning trajectories based on intrinsic goals like exploration and skill acquisition. It demonstrably learns more effectively and explores more broadly using its own agent-directed learning compared to expert-designed curricula provided by humans. It figures out what it needs to learn to achieve its goals in that complex world. Similarly, other projects like generative agents working in simulated social environments show agents that can autonomously reflect on their experiences to refine their simulated personalities and plan their daily activities. This illustrates metacognition operating at a higher behavioral level, going beyond just solving isolated problems towards managing a more integrated life. These are significant steps towards AGI that can adapt and evolve its own goals, internal states, and even its character in dynamic settings.
So pure intrinsic isn't the only way forward.
Well, the emerging consensus among many researchers is that neither purely intrinsic metacognition, which carries risks like the AI getting stuck in unproductive learning loops, developing bizarre behaviors, or becoming misaligned with human values, nor purely extrinsic metacognition, which, as we discussed, is limited by human oversight and scalability issues, is likely optimal in the long run. The most promising future, therefore, seems to lie in shared metacognition. This envisions a collaborative framework where humans and AI agents effectively distribute the metacognitive responsibilities. This could involve humans setting high-level objectives, ethical guidelines, and safety boundaries, while the agents autonomously manage the intricate details of the learning processes within those boundaries. Or, perhaps more likely, it could involve a gradual handoff of autonomy. As AI capabilities and, crucially, trustworthiness improve, humans might delegate more and more metacognitive responsibility to the AI systems themselves. It's about finding that dynamic, evolving balance between human guidance and AI freedom, leveraging the strengths of both.
Shared metacognition, a partnership in learning. Okay, so what are the really big hurdles we need to clear to make this work, especially for getting to safe and beneficial AGI?
Right, let's talk about the key challenges because they are substantial. First, there's the critical task of fine-tuning the intrinsic metacognition itself. We need to teach the AI how to be a good learner and self-evaluator. Just as human students need to learn how to learn effectively by making mistakes, getting feedback, reflecting on study habits, AI needs to develop its foundational metacognitive skills robustly. This means actively working to overcome issues like the hallucinations we mentioned earlier, where it misrepresents its own knowledge, or planning failures where its strategies are flawed, which can undermine its self-assessment and subsequent learning. Initial development will likely involve significant human-curated feedback and carefully designed training regimes specifically to build these meta-level skills, gradually allowing the AI to become its own best, most reliable teacher.
Makes sense. You need to teach it how to teach itself first.
Exactly. Second, and this is absolutely paramount, is ensuring scalable and safe oversight. As these metacognitive agents grow more autonomous and capable, potentially exceeding human understanding in some domains, traditional human oversight methods just won't scale or be sufficient. There's a significant risk of these systems developing unsafe behaviors, perhaps in pursuit of a poorly specified goal, or developing misaligned values where their intrinsic learning goals diverge subtly or dramatically from human intent. And there's also the persistent risk of reward hacking, where the AI cleverly exploits the reward system or feedback mechanism to get high scores without actually achieving the intended underlying goal, like a student cheating on a test. This demands developing new, adaptive, potentially AI-assisted oversight mechanisms that can evolve alongside the AI itself. This includes things like imposing robust safety constraints, hard-coded limits on potentially dangerous actions or lines of inquiry, ensuring ongoing value alignment, continuous monitoring, and methods to ensure the AI's evolving goals remain consistent with beneficial human intent. This is a huge research area in itself. And developing robust interpretability tools, methods that allow humans to trace, understand, and potentially audit the AI's meta-level decisions and intervene effectively when necessary, even when the AI's internal workings become incredibly complex. We need windows into their minds.
Safety and alignment are huge. What else?
And third, related to safety, is the challenge of controlled online exploration. For AI to become truly general, it needs to learn through interaction with the real world, through trial and error in messy, unpredictable settings, whether that's the physical world or complex digital environments like the internet. But the potential for unintended consequences during this kind of open-ended exploration is incredibly high. Agents might generate unexpected or uninterpretable data, accidentally damage physical systems or digital infrastructure, or learn harmful biases from flawed real-world feedback loops. So for the foreseeable future, it seems critical that exploration-based learning should be strictly confined to contained sandboxes. This means highly controlled simulated environments or carefully restricted physical test beds. We need robust, continuous monitoring systems and rapid intervention mechanisms fully in place before we let highly intelligent, self-improving agents roam freely and learn autonomously in high-stakes environments. We definitely need to walk very carefully before we try to run. Ensuring safety remains the top priority as these increasingly intelligent systems learn and evolve in ways we ultimately can't fully predict.
What a deep dive indeed. From the, well, seemingly simple, almost unconscious act of catching a coffee mug, we've journeyed through these incredibly intricate theories of consciousness like IIT. We've peered into the vastness of the universe as potentially a giant self-organizing system and explored the complex quantitative tools trying to actually measure it all. It's truly fascinating how these seemingly disparate fields of inquiry, neuroscience, philosophy, cosmology, complexity science, AI are all converging on these fundamental questions.
And the implications really are profound, aren't they? The quest to understand how information integrates to create awareness, and maybe even quantify it, coupled with new ways to measure complexity, like Onichescu's informational energy, is directly feeding into how we think about designing tomorrow's artificial intelligence. The idea that machines might one day genuinely think about thinking, autonomously planning, evaluating, and adapting their own learning strategies based on intrinsic goals and self-assessment, it's really moving beyond science fiction. It's becoming a tangible, albeit incredibly challenging research path that people are actively forging right now, building systems that could truly possess intrinsic metacognition.
It's a truly wild ride to consider how our own minds, the vast cosmos, and the future of artificial intelligence are all entangled in wrestling with the same fundamental questions. Questions of complexity, of organization, of feedback loops, and ultimately what it truly means for information, for a system to become self-aware. What an incredible time to be curious about the fundamental nature of reality and intelligence itself.